Okay, let's get started. So how was the CTF? It's good. Okay. I think most of you did quite well. Half of you got all 4 flags, and most got 3 flags. I think when I look at the grade at this moment, I do not really worry about yet. But if you have any concerns, let me know. I know some of you may be aligned students and you need a certain grade to graduate and you have a job lined up. Yeah, so I'm considering give more bonus points in the second half of the semester. But when I look at the grade, the homework, everything, I do not see anyone is failing the class right now. Okay. So if you keep the pace, I think everyone will be fine. So today we will keep talking about software vulnerability. And so far, all the vulnerabilities are there because we are using memory unsafe languages. And all the vulnerabilities we are exploring right now, they are memory safety issues. So memory unsafe languages are those languages that do not provide a built-in memory safe mechanisms. So developers can directly control over memory allocation, deallocation, reference, dereference, different memory addresses. Usually the performance is very high. However, it's too much power in the hands of developers. The C language, C++ language we're using, assembly, Objective-C, which you use in Apple computers. They are all those memory unsafe languages. And there has been a big push of memory safe languages such as Rust. Rust is relatively new. It probably has been there for 10 years or maybe a little bit longer, but got adopted in the recent 3-5 years. But if you say our legacy C code, it's huge. The Linux kernel is probably 20 or 30 millions of C code, right? So you cannot replace them with Rust overnight. Many reasons. First of all, performance. There has been many studies on the performance of Rust. It's not that bad compared to obviously Java or Python. It's not that bad. But also Rust also have some memory issues, not necessarily traditional memory safety problem, but other issues. And you have seen some examples of memory unsafe functions developed in the C library. Those are the standard library that are in standard C textbook, even the classic C textbook authored by the authors of C, they have bug safe, right? So those functions like string copy or even the safe version, string uncopy, they're not really safe before that, right? Memory copy. So you have seen those kind of functions already. Those functions, they have a very straightforward interface, copying something from a memory location to another memory location. Today, we're going to see some other memory unsafe functions. Their interfaces are much more complicated, but they can also be exploited because they also make memory safe issues. And the fundamental reason here is because the C language allows you to do that. No matter you are a developer or library developer or OS developer, you can make those unsafe operations, okay? Which means the C code you write, it is compiled into instructions. Those instructions will do things we're not supposed to do. Those problems can be addressed at different layers: hardware layer, operating system layer, compiler layer, and also language layer. Rust is trying to address that in the compiler and language layer. And our lab will do something at the OS or hardware layer as well. But today we're focusing on the language part. So the vulnerability we're learning today is format string vulnerability. And in the second half of the class, we are going to move a little bit faster. So every class, we're going to talk about one topic. We only have maybe 4 classes left, I think. Yeah. So we're talking about format string next week, Rob. Then after that, we talk about memory allocators, basically heap. Then after that, we talk about cache. So a little bit of history of the format string attacks. This was discovered in the summer of 2000, 24, 25 years ago. So if you remember the history of buffer overflow, the string copy, memory copy, those were discovered back in the 80s. So it takes another 15 years for people to discover this. But obviously the problem was there for a long time. So an issue was found in a Washington University FTP server, and there was a post on this bug trap mailing list. That mailing list still exists. Hackers still send their findings there, and also a lot of news on that mailing list. So this exploit allowed remote attackers to gain root access to systems running with that server without authentication. So this is another privilege escalation attack. The vulnerability, because that FTP server implementation was widely used, the vulnerability was severe. So, in short, this vulnerability or this class of vulnerability occurs when programmers pass externally or user supplied data to a printf or similar functions as part of the format string arguments. So all of you have been using printf or similar functions. So let's take a look later. So this vulnerability is also falling under the category of input validation bugs, because the user put some inputs there, and that input will trigger a bug. Okay, so this category is actually a very broad category. So the first half of the semester, those memory bugs also fall into this input validation category. You input something, and the input will trigger some bug. So the fundamental of this bug is because in the format string, it uses a C standard feature called variable argument list, or VA_arg, variable argument list. Using this feature, you can develop functions that take different numbers of parameters. So far, we have been, in this class, we have been looking at functions with a fixed number of parameters, except those printf functions, right? Printf functions can take many parameters. So it's a little bit different from buffer overflow. Technically, this kind of bugs can be easily fixed at the source code level. So before we look at this bug, so let's first understand what are variable arguments and how do you develop functions using this feature. Or C++ support this. A C function with variable arguments is where the number of arguments is unknown or not constant when the function is developed. When the function was written, the developer of this function doesn't know how many parameters there will be when this function is called. Okay. However, when the function is called, when the function is used, the user knows. Okay. So when you write a function call to printf, you know how many parameters you are giving to this printf, right? If you know as a developer, it means the compiler also knows. Okay, so this is not a runtime thing. It's only at the development time the developer doesn't know. If you want to develop a C function with variable arguments, you just need to include this standard argument library header. That introduces a type called the VA underscore list, okay? Variable argument list. And there are 3 other functions and macros that can operate on the objects of this list for you to retrieve the arguments. They are VA start, VA arg, and the VA end. Okay, those 3. So here is one example. Let's say we develop a function in C, and this function will compute the average of several numbers. Okay, but we don't know how many numbers are there. So this function name is average. It has the first argument here. We know the type and the name, which is int, and the name is number. Okay. However, the second argument, we don't have its type, we don't have its name, right? We just use 3 dots to represent that there could be many arguments. So if you look at the prototype of printf or any other format string functions, you will see they have the same print prototype. So we should do a man printf. So this is the command printf. Should go for 3 maybe? Yeah. So printf and all other format string functions, they have similar prototype. The first argument for printf, the first argument is a string. Okay? That is a format string. But the second argument and all others, first of all, we don't even know how many are there. Right? Because we don't even know how many are there, we don't know their type, we don't know their size, we don't know their names. Then fprintf actually can take the first argument will be the file pointer, the second argument will be the format string. Then you have other arguments. Okay. So going back to this average function, the first argument here is an integer. The second and others, we don't really know. Then in the implementation of it, we want to compute the average of those numbers. This is how we use it. We call average, and the first argument, we define it as the number of integers we want to compute the average on. So after that, we have those integers. So the first time we call this average function, there are 5 parameters. The first one is how many integers are there, which is 4. Then after that, we have 2, 3, 4, 5. Okay, so in total, 5 parameters. Second time we call this, we only give it 4 parameters. So the first parameters is the number, which is 3. Then we have 5, 10, 15. Okay. So as you can see that, as a programmer who uses this average function, it is your job to use it correctly. If you want to compute the average of 4 numbers, it's your job to set the first parameter as 4. If you made a mistake, then it will not calculate the correct average. Okay. Then let's look at how this is implemented. At the very beginning, we will define this variable argument list. Just use the standard, say standard. Then after that, we define the sum as 0, index I. Then we use the library function or macro, VA start, to tell the underlying library which parameter is the last parameter we know its name. Okay, so in this case, we have to use var list, which is this one. Then we tell underlying library number is the last parameter we know its name, which means after that we don't know its names, we don't know its type. Okay, so same thing as here in printf. The last parameter we know its name is format. for fprintf, the last parameter we know its name is also format, but not string, obviously. Then we can enumerate the other arguments using the other macro called VA_arg. Okay, and in this case, we need to know the VA_arg takes two arguments. The first one is varList, which is a local variable here. The second one is the type of the next argument. The int here means the type, means we know the type of the next argument is an integer, okay? And this is hard-coded in this piece of code. In printf, obviously not. We will see a printf implementation later. Then here we have a for function, or for loop, because we know how many integers are there. After we use all the variables, then we need to you call the var end function to say that's the end of those variable arguments. Okay. That's it. That's how you can implement a variable argument function in C. So when the first time we call this function, the stack will look like this. 32-bit version. We have, let's say this is in the main function, we call printf. Actually, we call average first, then we call printf, right? So in the main function, we have the return address, we have the saved EBP, we have main functions other data, if there is any. Then there are five arguments. 32-bit, we're pushing those five arguments to stack, right? So we have the fifth, fourth, third, second, and first argument. Then we have the return address, we have the saved EBP, and this return address is somewhere in the main function, and this is the stack frame of the average function. So the VA_arg will point to somewhere here. So, like I said just now, as a developer of using those functions, it is your job to make sure you use them correctly. Okay. So there are ways you can make all kinds of mistakes. For example, here, average 5, 2, 3, 4, 5. Okay. We're telling the average function, we are calculating the average of 5 integers, but we're only giving it 4 numbers. Say in this case. So in this case, because we don't really have the fifth argument, then some random data on the stack will be considered as the fifth argument. So you're not really getting what you want, right? So some of you may program in C++, and in C++ there is another feature called a function overloading. Basically, it means you can have 2 functions or even more functions with the same name. They have the same function name, but they have different prototype. Here, the prototype, we're not talking about the return value, but the parameters. Let's say in C++, you can implement 2 average functions. The first one is the average of 3 numbers. Okay, I, J, K, then you divide by 3. Another one is average, you have 4 numbers. Okay, so this is a totally different mechanism than the variable argument mechanism we saw just now. Okay, so this C++ mechanism will treat those 2 functions totally independently. They're not even related. They happen to have the same name at the C++ code level, but after they are compiled, they have different symbols. For example, after we compile this, the average, this is a C version of variable argument. C++, you can also do the same thing. Okay, variable argument, no matter how many arguments you have, that's one function. That's one average function. Looks like this. Okay, the symbol there you can see it's average. Okay, that's the name of that function after you compile average. So the right-hand side is the C++ version of function overloading. Okay, and we have two average functions there, and each of them is compiled into a different function. They're not even related, and at the symbol level, they actually have different names. Okay, as you can see that their function names are not average anymore. The first one is average III. So average is at the source code level, the function name you give. III is the parameter types. We have three parameters. They are all integers, right? That's why III. And how can you tell? Because they are concatenated together. How can you tell which part is parameter, which part is name? That's why we have 7 here. 7 means the next 7 the next 7 characters is the function name. After that is an integer, is a parameter type. Okay. So I think Z means the return value is integer. Yeah. Then you can say the next function, this function, it has a different name. It has III. And they have different code bodies. So they are not even related. So those are two different features. So to know how to exploit this vulnerability, then we need to know how to use those format strings. So first of all, format string functions, they are very popular. All of you have been using it. We use it to convert simple C data types to string representations. And it allows all kinds of format of presentations. And it can process the results to different places, standard output, files, logs. The format string itself actually controls the behavior of the function. So in the average example, the first argument, the number, tells that function how many integers are there. Okay. In format string functions, the format string tells the function how many parameters are there. Okay. And it's the developer's job to give both the format string and parameters. And that's where you can make mistakes. Developers can make mistakes. So in format string, you do not only tell how many parameters are there. You also tell the type of each parameter. So in the average example, we are not telling the type of each parameter. We just hard-coded everything to be an integer here. But in format string with %d, %x, %s, you're actually telling the type of the parameter. We already see this. There are many different format string functions, and some of them you are already familiar with, printf, fprintf, but there are others you are not familiar with, like syslog. There are some arrow things. They do not necessarily have the word print or f there. Okay, so they also use format string, and they are vulnerable to the same type of vulnerabilities. Okay, so then what is a format string? This is a C programming language. Format string is a special string. Every string is just characters ended with a 0, right? So it's a C string, first of all. It can optionally obtain embedded format specifiers. And those specifiers can be replaced by values specified in the following arguments as the format requested. Okay, so the format specifier has this prototype. Usually we just say a percentage sign, then just one letter, a D, a S, right? That's what you are familiar with. but actually it can be more complicated than that. There can be a flag, there can be a width, precision, length, then the specifier is a must. You have to have a specifier. And the percentage sign is basically the ASCII value of 25. So even if you do not say that as a percentage sign, but it's ASCII value of 25, it's equivalent. There are all kinds of specifiers, and you are familiar with many of those, like D, percentage D. D is decimal, means you want to print something, you want to print an integer, and you want to show decimal. You can print a U, O, X means hex, also float. So any of you notice something here that you are not familiar with? I think P, we already used that before, which is a pointer. We used it in the first half of the class. Which one? Yes. So anyone here used the N before? Yeah, you used the N before?
Yeah.
For hacking or for what?
I know, just coding.
Okay. For what? Yeah, what kind of use cases?
I don't remember, but there was a point where like from the output wanted to see how much is being printed or something like that.
Okay.
Yeah.
Oh, yes.
So for that time was
Yes.
Yeah.
Percentage N is actually exactly for that. So percentage N, if you use percentage N, printf functions were format string functions will not print out anything different from percentage D, percentage X. It will print out something. It will not print out something. However, the corresponding argument for percentage N is an address, is a pointer. Okay, and that the number of characters written so far in this function. For example, you do a print percentage, you do a percentage D, it print out 10 letters, character numbers, digits. Then you do a percentage N. So far, you have been printing out 10 characters. Then the number 10 will be written to that address corresponds to that percentage N. Okay. So this is very dangerous because you are writing to, by using this feature, we're going to look at more concrete examples later, but you can say that you are writing to a memory address anything you want, basically. You have an arbitrary write capability with this percentage N. Okay. So we're going to talk about that part second half of today's class. There are also flags, could be minus, plus, could be space, could be zero. They are for the fittings or paddings. Then it could be weights, like how many digits, how many bytes, characters you want to print out, precisions as well. Yeah. Also length. The length part, you can say you are writing an integer, 4 bytes. You are writing just 1 byte would be half of half, HH, okay? Or long. So let's say a concrete example. We have 8 different printf functions here. The first one, printf characters, percentage C. So each percentage C is the whole thing you can say that's a format string. The percentage C is a format specifier. C here means character, right? So we're printing out a letter. Then which letter we're printing out? The first percentage say we'll look for the next argument, which is a lowercase a. Okay. The second percentage say we'll look for the second argument. In this case, which is integer 65. So both of them is represented. Both of them are represented in numbers, right? This is computer, everything is a number there. So the lowercase a is probably 97 something. The uppercase a is 65. So that's why when you call this function, the output you get is lowercase a and uppercase a, okay? So this is simple, this is the first one. The second one, decimals, percentage D, we are going to print out just a decimal number. Then we can also print out a bigger decimal number here. We can do L, which is long in this case, means the input, the corresponding argument is a long integer. Okay, it's not integer, long integer. So this one determines the size and type of the corresponding parameter, basically. Right? The next one, proceeding with blanks. So here we have percentage D, which means we are printing out an integer. However, before D, between D and percentage sign, we have 10 there, okay? Let's go back to here. So 10 is not length, because length can only be HH to L, those things. So it's not length. So which means when there is no specifier for length, means this is just an integer, okay? So which means the parameter is just a 4-byte integer. And this is not precision, because precision requires a dot there, okay? So that 10 is actually width, okay? Not flags, because flags can only be minus, plus, space, pound, or 0. That's 10, that's a number, that's a width. Okay. It means we are going to, so this number is a small number. It only has 4 digits. However, we are going to print out 10 digits here. Okay. And we are going to fill that with spaces. That's why, as you can see here, this is output. Yeah.
If you said percent D10, then I would put the space after the 1977.
This one?
Yeah.
This one is the space after. We're talking about the space in front of this.
Right, but that's like the order of the arguments in that. Does that matter? I guess. So if I wanted it to read 1977 and then 6 spaces, would I do percent D10 instead of
No,
percent?
if you want to do after, if you want to have 6 spaces after 1977, you just put 6 white spaces there. Yeah.
Well, then why would I not just put 6 white spaces here instead of doing the percent 10?
This is putting in front of this. Like this here.
But I could also just put
Yes.
spaces.
But,
But
what if the number?
Depending on what the number.
Exactly. For example, the number could be 8 digit.
And if I wanted, so I guess the order of these is fixed and you cannot do, for example, 1977 and then padding after it. The padding has to come before.
Yes.
Okay.
Yeah, in this format, yes. So in this case, so after comma, there is actually 1 white space, which is here, okay? Then there will be 6 more extra white spaces, then 1977. Okay, that's the output. The next example is similar, but we're not using white space as a padding. Instead, we're using 0 as a padding, and 0 in this case is not width, is actually part of the flag. The flag can be 0. So in this case, you will say, we have a white space here. That's because we have a white space. Now after that, we have 6 zeros. Now after that, we have 1977. Then we can also do hex numbers and others. Let's skip this one. Also floating numbers. The next interesting one is a string. A string in the format we are using percentage %s. So which means the corresponding. So what should be the corresponding parameter type in this case? For percentage %s. Yeah, pointer. Yeah, pointer is an address, right? So in C programming, when you write something like this, this is always an address. the string itself is stored somewhere, and what we are used here is just the address. Okay, so the format string determines how many parameters are there, and for each parameter, what is the type for it? Okay, this whole thing is called the format string. This part is called the format specifier, and each one matches one argument. So here percentage say means the next two argument should be a byte. So this is a simplified implementation of printf. This is not the C standard library implementation. It's just a simplified version. Let's say the argument, the prototype, the first argument is the format string, and the function is not going to change that format string. So that's why we have a constant pointer here. After that, we don't really know what are the names and types of each argument. That's why we only have 3 dots. So at the very beginning, we create this var list. After that, we initialize format as the last argument. We know its name, okay? Then we try to read, dereference each byte, each character of the format. Yeah. If that byte is just a regular character, we just print out, right? But if it's a percentage sign, it means that is a format specifier. Then we are going to do something special. For example, if after that percentage sign, we have a D, then we know that the next argument we're looking for is an integer. That's why we code it as D here, okay? So in the simplified version, we're not implementing the flags, the weights, precisions, those parts. We are also not implementing percentage n, just showing percent ds. So if it's s, then we know the next parameter we're looking for is a pointer, is a char star, okay? It's a pointer. If it's say, we're looking for, in this case, a integer, or it can be a char. It's different implementation here. Okay. Then we just output that. Okay. So this is a simplified implementation of printf. The real implementation is obviously much more complicated than this, but this is a skeleton of that. Okay, another example. In this one, we are going to learn what is percentage n. We have a function foo, 2 local variables a and b, both initialized to 0. The first printf, we do a, white space is white space percentage d, then b is something, then a and b. So what is the expected output of this one? 0, 0, right? Because a and b are zeros. So a is 0, b is 0. Now we print out changing a and b, okay? Using printf, we can change the values of a and b actually, okay? So here, the format string is bracket changing a and b dot dot. So before the percentage n here, this is just a regular string, okay? So this part will be just the print out byte by byte. Printf function will not change that. The next format specifier is percentage n, okay? Percentage n will look for what kind of parameter? Huh? Yeah, percentage n will look for a pointer, an address, yes. If we're looking for address, so the address we're giving it is a's address, okay? So printf is going to write into this a's address. And what are we going to write? We are going to write how many bytes, how many characters this printf function has printed out so far. So how many bytes? From here to here, maybe 20, right? I think it's 20, yeah. So which means after this, a will have the value of 20, okay? Then we keep printing out 1, 2, 3, 4, 5. And those 1, 2, 3, 4, 5 are not part of any format specifier. So they will be just printed out. Then after that, we have another percentage n here, which is corresponding to the b's address, okay? Which means how many bytes we have been writing so far. So 20 plus 5, 25. So after this, A and B's value will be changed. But this 9 will not output the value of A and B. It will change that. The next 9 will change the value. Okay. So format SN. Okay. Let's try this. Okay, so this is the output. The first time we call printf, we print out A is 0, B 0. The second time it print out changing A and B 1, 2, 3, 4. So in that format string, there is a percentage on here, another percentage right here. Those two doesn't print out anything, right? So after that, we print out AB's value again. And now AB's value has been changed. We got A is 20, B is 25. After that, we change A and B's value again. Let's say in this case, changing A and B, and we know this is 20 bytes. Then we have 0, 20D, okay? So which means we're looking for an integer, and that integer is number 50. But how many bytes we're printing out here? We're printing out 20 bytes or 20 characters, and the first 18 will be 0, right? That's a padding of 0. Then we're showing 55, 0. Okay. After that, there is a white space. Okay. So that's another white space. Then we have a percentage n. So how many bytes we have been writing so far? 41, right? That's why we write that 41 to the value A, then another percentage n. And before that, we didn't print out anything, which means we're writing 41 to B2. That's why both A and B will have the value of 41, right? So the last call to printf, changing A and B again. This time we print out a floating number. The precision here is .2, means 2 digits after the period. Before that is 10 and with 0 as padding. Then there is a percentage n. So A's value is changed again in this case. And so A had a value before 41. Now A is going to be overwritten. In this case, it's 20. I'm not sure how big this is. This is 8. Yeah, anyway. So let's say. So A's value eventually was changed to 38 in this case. Okay, so this is the percentage n format specifier. I never had a chance to use this except for hacking. I do not have legit reason to use this. Okay. There is a POSIX extension of percentage n and format string, which is the $sign. In this class, we do not really hack this version of it, but it's actually also very simple. The idea of this is you don't need to, if you have a parameter you want to use multiple times, you don't need to repeat that. For the regular format string, if you, because each format specifier matches one parameter. If you want to use one parameter multiple times, you need multiple format specifiers to match each of them, right? The idea of this is you just use the dollar sign and a number before the dollar sign to tell printf which parameter you are using. For example, we have printf percentage $2 D. Okay, since this is D, it means we're printing out an integer, and which parameter we should look for? We should look for the second parameter after this. So $2, which is 70. Okay. Then you reuse this again, but you do not print it as a decimal. You print as a hex value of that. That's why you use X. However, you are still using $2, which means the second parameter. And here you do not specify 17 twice, just once. Okay. We're not going to hack this version. Okay. So what could go wrong here? What kind of a vulnerability we could have in this kind of functions? The format string and the parameters are both specified by the users. That's where the problem could be, is the format string should be hard-coded, okay? But the user can directly put their input into the format string. If your input is directly used in the format string, then your input can determine how many parameters will be used, right? So previously, the format string is hard-coded. So how many parameters are used is determined when this function call is made in development stage. When it is compiled, it's hard-coded. But now you specify this as a user input, and the user input will be different each time you run the program. Then how many bytes, how many parameters will be used is only determined at the runtime, not compile time anymore. So the coder can provide can use more format specifiers than the parameters that are inputted there. If we do that, it means the printf function will look for some garbage on the stack. And we know that not everything on the stack is garbage. There are return addresses, there are local variables, there are stack calories, right? Then you can dereference those values. So the run usage of this is a user controlled string. You directly use that string as a format string. Okay. The correct usage of this is you should hard code this format string. That's why some people say this bug can be easily fixed. You don't need to change too much of your program. You can easily fix this bug. This is our very first example. We're going to hack this one. For this example, calorie is enabled. Long execution of stack is also enabled. So this one, we're not trying to get the flag actually. This is just a demo. Okay, so we have waffle. We have a buffer, which is 20 bytes. Then there is a printf. What's your input? Any vulnerability in that printf? What is the vulnerability? It's the first printf.
We can put whatever we want.
No, the first printf.
Oh.
Is there any vulnerability?
No.
Not really, right? Because we're not using any format specifier there. Then we have gets. Then we are getting input from user from the terminal, and there could be a buffer overflow. Okay. However, calorie is enabled here. Even though there is buffer overflow, you cannot easily hack this one. Then we have another printf, and this printf use your input. In this case, could be bigger than 20 bytes, and use that as a format string because it has only one parameter there, and the first parameter is a format string. It's using your input as a format string. Then what can we get from this? Let's say this is format string 1. Okay, so what can be our input? Our input can be just a regular hard-coded string. If it's very long, it will trigger that calorie. Yeah, so stack smashing detected. If it's smaller than 20 bytes, it will not do that. Okay, so what kind of attacks we can conduct here? What can we do here?
Print out the canary.
Hmm?
Print the canary
Print out the canary. How do we print out?
by specifying more than 20 format specified
Okay, why do you need the 20?
to fill the buffer.
You are right that we can print out the calorie and we can print out whatever is on the stack. But that number 20 may not be correct there, but we can talk about that later. Anyway, so percentage what you want to use here? C, okay. What is a calorie? How long is a calorie in this case? 4 bytes, right? So you can use percentage D, you can use percentage X, doesn't really matter, right? Let's say we do percentage D, we do percentage X again. So we are getting, this is our output. We're getting some numbers there, okay? And the first one is a lective number. Let's try this again. So how do we make this more clear? You can see, it's not clear. Yeah, we can do space. We can use any kind of a delimiter you want, right? We can do a space here. And we get 3 numbers here. The first one is a lective number, then a 0, then 5, 6. This one. What is this? This looks like a code address, a pointer, right? Looks like that. So maybe we just do percentage X. Oh, percentage X. Okay. So this is what we get. So F7, this also looks like a pointer. This looks like maybe save the EBP there. Could be. Looks like a stack pointer. Then there is a 0. What is that 0? I'm not sure. Then that number looks like we can do many more. So we have a 1 there. Then this also looks like a pointer. Okay. So that's percentage X. So how do we crash the program? Can we crash the program easily? We just want to crash it. What kind of person?
You already crashed it by just filling it up with stuff, because it.
Yes, yes. I mean, use a format string. How do we crash this? To crash a program, you can ask the program to read a memory that it doesn't have the right to read, or write to a memory it doesn't have right to write, right? So percentage N, percentage S, both possible. Let's try percentage S first. So in this case, percentage S didn't crash the program. It print out a string there, which is UW. But if we do this multiple times, it's very likely, here. Anyway, there was a 0, right? So the first one is this address. The second one is 0, which means we're going to read memory address 0. And that's not readable. So the second percentage S should, in this case, it doesn't crash. It just should not there, right? That's almost equivalent to crash. But what if we write to that place? Then we got a segmentation fault. We're trying to write to that location, right? So if we look at the stack carefully, try to understand what's going on here. So the left-hand side is the disassembly of this, and I draw the stack based on the disassembly. This is the beginning of vol foo. So we have the return address. Vol foo doesn't really have any parameter, so higher than that, we don't have parameter. We have saved EBP. We do have calorie here. We don't know the value, but the calorie is at the address of EBP minus 12, which is say here. Then we have S, that local variable, 20 bytes in say code. In the assembly, we checked it's actually exactly 20 bytes. After that, it's the calorie. After that, vol foo will call printf. We do not know the exact implementation of printf, right? We're treating it kind of like a semi-transparent box. We're not trying to understand every line of code of printf, okay? But we know at a high level how it works, which means we don't know exactly how many bytes are here on stack, right? We know at some place the printf, because the printf has only one parameter, which is printf s, right? So we know s, the address of that string, which is s, is pushed onto the stack. But we don't know the offset from here to here, okay? Because print, there could also be something in between. In vol foo, we didn't really check that part. Okay. Then lower than that, we have the return address. So this is a printf stack. Then save the EBP. Okay. Then S, when we input percentage X, Y space percentage X, this 20 bytes will have that string. The S here is a buffer, okay? It will have that string, the value of that string, because we get the value into the local buffer S, okay? Not the address of that, okay? In this case, from printf's point of view, it believes it has three parameters, right? The first parameter is the format string itself. The second parameter is an integer mapping to corresponding to the first percentage X. The second is the third argument is the second percentage X. Okay. However, we never pushed that onto the stack. In our source code, we didn't do that. Okay, we only do printfs. We didn't do printfs, integer 1, integer 2. We didn't do that, right? And this cannot be detected at compile time, because compile time you don't have that format string. Format string could be user input. Only runtime have that, right? So from printf's point of view, those two, the second and third arguments, should have a higher address than the first argument, right? That's it, okay? Even though we didn't put it. So by putting a lot of percentage X here, we will be able to read everything on the stack, right? So if we put percentage S there, instead of treating the second and third arguments as an integer, we are treating them, each of them as an address, a pointer, okay? And we are going to dereference that pointer and print out the string at that address. And if that pointer is an invalid address, an address that is not mapped in the process, there will be a segmentation fault. If that address is mapped in the process, however, the current instruction doesn't have permission to read that, we also get a segmentation fault, right? If we have percentage n, the same thing. Instead of reading, dereferencing, we are going to write to those places. Okay. Okay. So the second example, there are two secrets there are two secrets in the program, which I'm not going to show you in the source code. And it's your job to get the secret. You have to use a format string. You cannot debug to figure that out. Then the main function first print out the secrets are at P1 and P2. Give you the two addresses, okay? Then it will call the val foo, and the val foo will take your input and use your input as a format string. Okay, that's it. So think about how to do this. This may not be that easy, but I give you several minutes to think about this.
You can input the addresses first
Okay,
in the buffer,
okay,
and then we'll also have to find out where exactly the buffer starts
yeah,
from the point of the vulnerable function, so that we'll know which argument we want to look at.
okay,
And then we can give something like %s.
okay.
And we also have the option to, like, select which argument we want. Like,
We're not using that option, yeah.
okay, I
You're
don't
talking
think,
about the dollar sign,
yeah,
we're not using that.
I think we won't need it here, but
We
yeah.
don't need that anyway, yeah.
Yeah, here we can give like percentages such that it should point to the start of the buffer. And then it
How
will,
do you find out the exact address? Because it's inside printf and there are other functions.
So, kind of brute force here. Like for the
Okay.
previous one, I saw it was in the sixth variable.
Mhm.
So if you just keep doing %x many
Okay.
times, at one point you will see the percentage being printed, since it will reach the buffer.
Percentage be printed or,
Like 25, the hex value.
okay,
Yeah.
Mhm.
So if I see for this,
that makes sense. Yeah, you can try. First of all, we disabled ASLR here, so the address do not change to make things a little bit easier. So even if you change, you can, with pound tools, you can write some script to do that, to make things easier. You almost fall asleep there. So you input this by piping something into the program, okay? Your idea is to use %s to print out two strings. But %s will look for two addresses. Okay, so somehow you need to put those two addresses onto the stack, right? And find those two addresses. I give you 2 more minutes. Alright, cool, okay. Okay, so let's see how we do this. Print. So we want to put those two addresses on the stack first, right? Let's try one first. 08 70 56. So after that, so this string will go to that local buffer, which is involved. And printf will look for parameters from a lower address. So we want to find out from where. So we do a lot of %x here. So when we do %x, eventually we should see this number, right? We should see this 5655 number. Let's see.
Here it supposed to be.
I forgot to. Oops. Ah. Oh,
The double percent, something.
this should work.
Python's interpreting it as a format string before it prints anything.
Ready? Why is it keep doing this? Anyway. I'll separate those. It's basically equivalent, so. And operator of the string. What's going on here? Why is there a percentage? That's my inputs. Okay, that's actually correct. Okay, do we find our number there? Not yet. So we print out 4 numbers on a stack and we do not see the number we put there. So we just put more, print out more. X. What's going on? Oh. Let's print out 8 numbers there. So we put out 8 numbers there.
Is it 56557?
Yeah, this one, right? So which one is this?
5.
So what is PUV here? What's that? That's part of this. 565570. 56 is P. Because this is the format string we input there, right? So eventually that is print out. So the 8 is not printable. 8 in hex is not printable. That's why we're not seeing it. However, 56 is P, no, 70 is P, then 55 is U, 56 is V, right? That's why we're saying PUV there. Then after that, we have percentage X, right? So we are getting the 4 bytes higher than the format string's address. Use that 4 bytes as output, as an integer to print out. And we are getting this FFF D6 right? So, which means this percentage X corresponds to this value. The second one corresponds to C2. This one corresponds to this. And this will be the 1, 2, 3, 4, 5. The fifth percentage X actually corresponds to this value. And what is this value? This is this value again. Is at 5578 again. Okay. So that was actually printed out twice. The first time printed out as the beginning of the format string. The second time printed out as a parameter. Okay, make sense? Okay. So if we change the fifths, 1, 2, 3, 4, 5. So if we change the fixed X to S, we should get the first string. Okay, so we get this is a secret. Okay. So if we want to get the second, we want to get the second string too, we put another address, which is a second string's address, which is 1A 70 5556. Okay. So after this, we should have another percentage S. Is that right? Maybe. Because we, yeah, should be right. Okay. That's why how we get this is secret 1 and this is secret 2. Okay. So say we have the ability to read arbitrary address in the memory space. Okay. We have that ability now.
Is 1A also non-printable?
Yeah, it's a very small number. The printable start with maybe 20 something or 30 something. And ASCII table. So 1A is yeah, it's not printable. Yeah. So that can you see it? Yeah. Okay, let's say. So the stack will look like this. This is awful. There's a return address, saved EBP, corollary, the temp buffer, which is 120 bytes. And in the temp buffer, we have our addresses 1 and 2. Addresses are just numbers. So some of those bytes can be printable. Then we use something like this. Percentage X. Eventually, this percentage S eventually corresponds to this address, and this percentage S corresponds to this address. Obviously, the order doesn't really matter. You can flip it. Okay, the next challenge we're going to do is format string 11. Corollary is still enabled. There is a print flag function in the address space. The main function takes 2 arguments. This function takes input from command line arguments and also a file, just to make it easier for you here. So you don't need to write code. You only need to write some exploit. So it checks whether there are 2 arguments then it print out where the flag is, the print flag function is, then it calls buffer. Buffer has a local buffer 20 bytes, has a fire pointer initialized to 0. It has printf argument 1, which is your input. This is where the format string vulnerability is. Then let's just print out a new line. Then there is a while loop. The while loop will read input from this temp exploit file. It will read 100 bytes from that file. It will read to the buffer. Okay, so stack clearly is enabled. If you write more than 20 bytes, not exact 20 bytes, I'm not sure. You need to figure that out. If you write more than that, obviously you get a segmentation fault, right? Which means by using this F rate, you will not be able to directly overwrite the return address. Okay. Print flag is in the address space, which means the goal here is to overwrite the return address. But the vulnerability you have here will overwrite the canary. Okay, so the goal here is use the format string to figure out what the canary is. Then write the exploit in this file. Then it will then overwrite the return address to print flag. Okay, so you don't need to inject any share code here. Make sense? Okay, I give you maybe 20 minutes on this one, or as soon as the first one capture the flag. You'll find the clarity.
Yes, I found the pen.
Got it?
Something there, or forgot the.
Oh, the fact.
Can every value be changing every time we run the program?
Yes. So there is only one value, it's changing every time, so that's clearly the query.
Yes. And then.
Got it? So where are you at?
That exploit, but then what does FG do?
You were using
This same-
Tmax or what?
Yeah, T-Max.
Okay, somehow Tmax is not working. It's not because the exploit was not successful, but it's just the output was not showing. That's why I switched to, I was using Tmax and it was not working. That's why I changed to background and foreground there. Yes. Okay, so let me show you guys how to do it. So first we run this program, right? We run it multiple times and you can clearly see that one value is changing, and which is this one, right? And that's a calorie. Actually, the calorie will be used by every function, right? So you can see this value multiple times on stack. You can see here. We see this value again. Okay, so at least we see it twice already. So that's a calorie value. Then the program will be reading input from the temp exploit file. So what I do is I do Control Z. When I do Control Z, the current program will be forced into the background and paused there. Now we create, we do another Python script. This one will put the exploit into the file with that calorie value, which is F200. So how do we get that value? The buffer is at EBP through through OBJ down. We found the buffer is at EBP minus 32 bytes. Then calorie is at EBP minus 12 bytes. And at C code level, the buffer is 12 bytes, and exactly that's what we get, 12 bytes. So we need 12 bytes of padding here, 4 bytes of calorie, another 8 bytes of garbage padding, another 4 bytes to override the saved EBP, then return address. Okay, the return address is print flag, right? So that's why we have 12 bytes, 20 bytes of garbage, calorie, 12 bytes of garbage return address. Okay, so we do this one. Now that exploit is into that Python, that temp file. Then we use FG to bring the only program running in the background to the foreground. So when we do this, then that program keeps running. That's how we get this. So Tmax, I think there is some redirecting issues. I'm not sure what exactly the issue is and how to fix it right now. That's why I switched to the background foreground part. Okay.
I had the exploit, I just was using Tmax.
Yes, yes. Yeah, I think the exploit was right. I was trying that, why it was not working there, and I think exactly Tmax thing, yeah. Okay, so let's take 5 minutes break. When we come back, we talk about how to do arbitrary write with this. Maybe we come back at 7:55. 7, 8 minutes.
Mhm. It's always a dollar. Favorite snack when I was like way younger used to be that Arizona iced tea and a bag of salt and vinegar chips. You get every taste. You get sweet, salty, sour, crunchy. When I was in break.
Yeah. Yeah, like this. Yes. Consonant.
Mhm.
Consonant.
Oh, where's that?
Um, I-
Me either.
So close. Think I mentioned.
Oh, wow. Like literally. Really?
It's all different.
When you get there, it's just like red line.
So. I took the 36 minutes. And it went to Chile. Lots. And then I took the night. And okay.
Really cool. I've been to like some of the islands before. There's a ferry that you can take in the summer. They have like. Spring. Boards are like a lot smaller than you think. They're like. I always thought they were like big.
I think you'll do it.
They are, but like they're very. Very low. That's cool. I feel like I haven't seen it from Boston. Yeah, but I've been here like a long time, so it's kind of embarrassing.
So we will really be financial.
It goes for Boston.
Have you been to the? So that.
Yeah, I still.
Maybe on this.
Well, yeah, I've registered in different times. I've registered.
Yes.
Right. I've been
Bunch of.
everywhere here, obviously, not here. Everywhere here.
So cute.
I feel like here, Middlesex Falls is awesome, like all of that. I've seen all of this area. Yeah, because it's like really annoying to travel there. I have to. One of my friends lives in Boston. It's also really annoying to get. So I've been here sometimes. This is where all the beaches are. in Boston. Or not all of them, there's obviously beaches here. But these are the ones we'd go to like freshman year. But my big mistake is I've never been. I've actually never been to Maine. Never. Just kind of stupid, this really should go.
I don't think I'm.
Nantucket. I've heard of it, I've never been there. Oh, yeah, okay.
I mean, not really. My question was whether the order of the flags were. And the answer was yes.
Just because.
I don't actually say what reason.
Yeah. I
Never read it, is it
I
good?
think I.
Is it good?
I've learned a lot about full history.
Yeah, never been to Nantucket, but, it's good.
I'd rather see.
Senior
it first.
It's also an island. It's like the other one. I don't really ever been to like actually, like, I've never even been to Pizza.
That's right, just like.
Yeah, no, literally, that's what they're made, 100%. I've never even been to Pizza. I've only been to like this one. You're gonna go to town and I traveled here, you stayed for like a weekend. And I opened the car door into my face.
Yeah.
And like, it was like, no problem. And then we like spent the rest of the weekend finding a dead. It's like,
We have a lot to talk about for the override part. Probably skip the first one, we're just talk about the idea, and you can do it in work. Don't worry, focus on others. So the first one, format string number 3. So we're turning this format string vulnerability into buffer overflow exploit in this case. Monfu has 2 buffers, buffer 1, buffer 2. Buffer 1, 100 bytes, buffer 2, another 100 bytes. Then we have fget to buffer 2. And the fget here is not really vulnerable. We're only getting 99 bytes, okay? So they can fit in buffer 2. Then after that, we do a s printf, and the format string is in buffer 2. The destination is in buffer 1. Okay. So the format string can be at most 99 bytes here. That's your input to buffer 2. That's the format string. Okay. If the format string is 99 bytes, how long will be the eventual string it is going to expand to? How big can it be?
Well, it depends on what flags we use.
Yes.
So if it was like %X and 32-bit, then it'd be 99
Yes,
before.
you can use that padding, so it can be huge, basically. It can be much, much longer, bigger than 100 bytes. So using that, you can overflow buffer 1, right? This one, calorie is not enabled. Execution stack is not enabled. So you can just inject the share-code into the stack using. So the share-code can actually be part of your format string. Then later it's expanded to buffer 1, overwrite the return address, everything. Also, you can put your share-code in environment variable. Okay, so this everyone gets this idea, right? This should be a simple one. We will skip this one. So the next one we're going to look at is format string 5, and we're going to use multiple approaches to hack this one. First, we have a global variable auth. It's a global variable, not on stack. It is initialized to 0 here. However, if it's not 0, we're going to print the flag for you. So one of the goal here is to overwrite the global variable auth. Okay, we haven't done this override, but you know %n can do this job, right? The valve foo, I put a little bit of assembly there, but don't get scared. It's there to help you actually. So that's not the part you want to hack. That's a part that to tell you where the return address is at. Okay, so it's to help you. There's a variable called stack. Don't really do anything. I'm just use the address of that variable to get the address of the return address, then print it out. Okay, so the real thing happens here. There is a buffer, 512 bytes. Then you have a fget to input into that buffer from std_in. So there's no buffer overflow here. However, that buffer is used as a format string. Okay, the same thing as the previous one. Except this one, I think we have clearly here. Anyway, even if there is a clearly, you know how to bypass clearly. So 2 ways to hack this. I think there's no clearly. One is you overwrite the global variable auth, right? So it print out. So the program will print out flag for you, or you overwrite the return address on valve_foo's stack frame. You change that to print flag. So the program will also print out the flag for you. So let's first use to overwrite the auth variable, because I want to show you how %n works. If we look at the disassembly, the buffer is this size, 524 bytes there. Then we can put, because this buffer will be treated as a format string, so you put the format string at this buffer or at the beginning of this buffer. Then you will have so what do you put in the buffer? You want to use that %n, okay? So similar to what we did with %s before, when you read the secret, you may want to put the address of that global variable auth at the beginning of the buffer. Then you do a lot of %x to find out which %x corresponds to that address of auth. Then you switch that %x, replace that with %n. Make sense? Okay. However, before that, you need to output something. You need to print out something. So when you do %n, it's not going to write 0 to that address, instead something else. Okay. In this case, we don't care what that value is. As long as it's not 0, it should work, right? So that %x actually will print out something. So that's very convenient. So let's try this one. Format string 5. So in the buffer, we want the address of auth, and to get the address of auth, we can just do an n. So auth is at this address, okay? It's a global variable. Let's just input from it's so std. That address at the beginning of the buffer is 34, say 0, 408. After that, we just put %x, put eight of those. No, type into the program. Shows us the return address is at this place, and also we are trying to find our value, which is this one. See, this is 1, 2, 3, 4, 5, 6, 7. The seventh percentage x. This will be 6. Then we pass. No, what was it? I'm trying to do percentage. That's it. Yeah. Okay. So after this, we're writing some value. We're writing actually. So here is 3. That's 18. There is 4. So actually, we're writing 22 to that global variable os. But in this case, the value doesn't really matter. Okay. So this is how we get the flag. If we change this to 5, then we are not really overwriting to that global variables address. We're writing to 0. Yes. We're using this value as the address, right? So we should get our segmentation fault. Okay. So this one is simple. Then a little bit more complicated version. This one. Overflow format string 6. The idea is the same. 2 false variables initialized to 0. Now you need to set their values to specifically to 60 and 80. Okay, not just long 0. Okay. To make your job easier, I print out the value. Oh yeah, I print out the value for you. Okay. So you don't need to, you just need to manipulate your export. Okay, I give you guys maybe 10 minutes.
Can you go back to the terminal?
Sure. This one. So you find the global variable of the address of 2 global variables. Put those address in the front of buffer. Try to use a lot of percentage x and say which percentage x corresponds to each address. Replace that with percentage n. But a little bit tricky here. You have to put a specific value in. How do you put a specific value in those 2 variables? How do you do that?
You have to have the right number of characters written beforehand.
Yes. So how do you can basically play with the width of that percentage x there to change that. What if the value get too big? Let's say not too big. Let's say because the number of the value you are inputting is always it's incremental, right? Let's say you already get a big value there. How do you get it down to a smaller value?
Up the size. Smaller, like specify.
No, for example, you already put, let's say the first byte you put is 80 bytes. That is 80. Then you already output 80 bytes. But the next value you need is 60. How do you do that? How do you get 60 out of 80?
Or 6, go back.
Or do I go back? Or
You just have to do it in order.
you don't have to. But I mean, there are cases you may want to. So if you are in those kind of scenario, how do you do it? What do you mean by go back? You are close there. I just want to know what do you mean by that?
I don't really remember like you can like go back to certain like rate cursor. Not that cursor like.
Ah, okay, that doesn't work. Okay, so remember that we talk about lengths. You can write a byte. You can write 2 bytes. So if you only write 1 byte, what is the maximum number you can write? 255, right? then how do you, now you are already at 80. If you can only override 1 byte, how do you get 60?
Like, go over 255.
Exactly, you overflow that byte. Yeah, you overflow that byte, then you can, like, you get 60 plus 256, yeah, 316, then you actually get 60 byte, 60. There will be challenge for that, but let's do this one first. This one, you don't really need that. So several of you already got it. So the idea is quite simple. You put those two addresses at the beginning of the buffer. Have percentage X there, eventually find out how many percentage X you need. Then you can add some paddings in between. So here I was doing 60 first, then 80. Let me show you the overflow one. So this one you can see works. I put the first one I'm using the auth, the second one is auth 1. So first one is 60, the second one is 80. So if we swap those two addresses, since we're a little bit different here. This one, here we need here we have 11 or oh, this is correct, right? Auth is supposed to be 60. Yeah, auth is 60. Auth 1 should be 80. Then
Although would be 34 and 38.
oh, so this one is auth 1. So we do we'll do 80 first. So
No, the order should be.
I'm trying the other order.
Oh, the.
Yes.
Overriding.
Yes, so this one should be 51. Okay, yeah, this one is correct. 51. So here, we're supposed to do. So far, we've been writing 100. We want to get to 316. So we need another 216 here. Will this work? It should work. It doesn't work because we get two, even this number is not correct. We should be a little bit higher. But still, this one is not working. Why this is not working? We're not writing 60 there. Instead, we're writing 316. So we're not only writing the last 8 bits, right? We're writing one more bit there, which we don't want to write. So the problem here is we're not really overwriting it yet, because we're writing 4 bytes. We're overwriting only if we're writing 1 byte. So to do that, because the percentage n, we're overwrite 4 bytes. We only want to overwrite 1 byte, so we do HHN. Okay. H is half. Half of half is 1 byte. Okay. So when we do 1 byte, then we're overflowing that. Then we get 60 there. Okay.
So I was wondering, is the reason why it's 31 because %x counts as 4 bytes written?
Which one is 31?
So, sorry, if you go up to the original one, 51 is also a good example, but
This one.
yeah,
Okay.
so it's 31 because %x counts as 4 bytes.
It's a little bit tricky here. So the percentage X here have different lengths for each output. You see, the first output is only 3 bytes. The second one is 8 bytes. The third one is another 8 bytes. Okay, if you really want to make it consistent, you instead of doing percentage X, you do percentage 0.8x, yeah, or 0 or 8x, make it consistent. Yeah, so here I was not trying to even fix that part. I was just adjusting this part to make it work.
That makes, I was just
Yeah.
curious why.
Yeah, that's a good question. Yeah. Okay. So now we go back to overflow 5. But now this time we're not overwriting that global variable. We're overwriting the return address. Okay. there is a challenge here is the return address. The return address in this case is 4 bytes. Obviously, 64-bit machine will be 8 bytes. And the return address will be a big number, right? It's not that big. It's 0804 something because it's code in the code region. So it's not that big. It's not FF something. So we can still overwrite 4 bytes in one shot, but the execution of that exploit will be longer. It will print out. So basically, we're printing out 08. How big is that? So the whole thing 32-bit is 4 GB, which is 4 GB is 4 billion, right? So 08 would be still like 10 million or something, I guess. Yeah, maybe 10 million. So we still need to print out 10 million characters in the screen. Okay, it may take. We're running this on a powerful server. It may take 20 seconds, but imagine you run embedded device. It may take forever. It may crash. Who knows? Okay, but we can try that. So go back to format string 5. We overwrite the return address there. 32-bit, which will be easier, but the idea is the same. Run the program first. So it gives us the return address. So return address is at that place, but we are going to write to print flag, right? Print flag. So print flag is at this place. That is a value we're going to overwrite to the return address. So address. The address we are overwriting to this place, so will be 8C D6 FF. From here, we're trying to find out we get this. Correct. Times this into this web. Get 8C. Not yet. Oh, this one may be big, right? Because the buffer is huge. Yeah, but we're looking at the beginning of the buffer, so it's not going to be too big. What?
It's the 7th one in, right?
Oh, yeah, it's here. Okay, so 7th. Seventh. So the 7th, we will need percentage n here. However, this one we need 6 of those. And now we want it to be very. Let's do 9. So when we do 9 here, then 6, that's 60, right? Because there is also a dot. So that's 60 bytes. And the value we're trying to write is this huge number. Is this number. big is it? Let's see. That's 30 million. Okay. So we need this number. So we already have 60. We need another 30 million minus 60.
Right?
What?
It's 64, right?
This is,
Because we were
The first
address.
oh, yeah, 64, you're right, another, so this is the number we need. So we just need a garbage, okay, times this huge number. Then we have percentage n. I think the calculation is correct, let's try. Oh, broken pipe. Maybe it's too big. Doesn't allow us to do that.
Try writing it into a file and then reading from the file.
Let's try that. Of course, we can write byte by byte, use that overflow technique. But that will make our exploit more complicated, but it will also be much faster. This one, let's say, let's try to override this. So this is, okay, this will work actually. Okay, this would work, takes, okay, 30 seconds maybe. Okay. We write this to a file. Wait. We cat this file. Okay. Looks like it's the pipe. Pipe doesn't allow this the line. Let's try. What's going on? It executed. No, I don't think. I think we'll probably get the same problem before the pipe thing. Yeah, looks like we get a broken pipe here.
The amount of characters equal to the address. I never caught why this is happening.
Equal to the number of address. Yeah, the equal to the number of address we are returning to. Because percentage n will write how many bytes printf has been that how many bytes to that address. That's why we put that word. Yeah.
What if we use that 13 million string as a format specifier? So we say we want the length of one of the %x's to be
Exactly.
13 million.
Exactly. We'll get back. Okay. So, let's say. Oh. That might be the same. That may also give us the, but it's worth trying. So we have percentage. X. We get 5 of this. The last one, we get this number. Well, it should not be this number anymore, right? So this is 50. This is 58. This is 54. Should be this number
That
minus.
should be the old number plus 10. Should be the old number plus 10.
Would be. Oh, yeah, the whole number, yeah, you're right. Yeah. So this number. try if we get a broken pipe this time. But this will also give us a huge number there, right? So may have the same issue. It's directly piped into the program. Well, it works. Yeah, it's not that bad, right? So we actually print out 30 million characters in just 6-7 seconds. Not that bad. But obviously the other approach is use the overflow approach. You write each byte, then you need 4 HHN there. Okay. So either or it works. Okay, that's overflow 5. So if you run a similar solution on your own laptop, it may take much longer. Our server is very powerful. That's why 6-7 seconds. I think when the first time I teach this class, we were using a virtual machine, not a server. Each student got a virtual machine, and that takes like 2, 4, 5 minutes to get this flag. That's why I also say we can use the other approach. The idea here is the same. This one is actually similar, except that we have 3 large numbers: dead beef, coffee, beef face. But you can use the same approach, just override those 3. But the number is much bigger than that 0.8 thing. So D is billion, several billion, maybe 3 billion. Okay. So you may have to, it still works, I believe. Will be slower just. So we will skip this one in class, and you will do this as a homework. Okay, so there are many other things we can overwrite. Okay, so now you have a very powerful tool. You can read arbitrary address in the address space as long as that address is readable. You can also write arbitrary address in the address space as long as it's right. Okay, which means there are many code pointers you can overwrite. You don't just have to overwrite the return address on stack. You can overwrite the C++ virtual tables. So each C++ class at the beginning in its implementation and its beginning, it's a virtual table. Virtual table is the function addresses, all of its virtual functions addresses. Okay, you overwrite one of those, one of these get called, then you can take control. You can overwrite the fili section. There are some library functions address you can overwrite. There is a global offset table. There are many library functions address you can overwrite, right? So I will skip the lazy binding part because we already talked about that multiple times. So the next challenge, format string 12. Calorie is enabled. Stack is not executable, which means you cannot inject the shellcode there. Calorie is enabled means you may want to bypass that. And print flag is in the address space. The problem here is the main function. In the main function, there's a local buffer. There is a first printf to show you where is print flag. Okay. There is no vulnerability here. Then there is a fgets to take 198 bytes to buffer. So no vulnerability here. Then there is printf using your input as the format string. That's where the vulnerability is. So with this vulnerability, you can override the return address, right? That's what we just did. You can override the return address of the main function. However, the main function doesn't return. That return address will not be used because the main function calls exit. Okay, how do you solve this one?
Change the X functions to global table.
Okay, yeah. So, did you guys get that? So exit is a C library function. Its address will be stored in the global offset table, right? So because of lazy binding, the first time exit is called, before the first time exit is called, its address is not really in the global offset table yet. It's a placeholder address there, and that placeholder address goes to a C library stop, which resolve the exit function's address at runtime, right? So the second time you call exit, well, it works for other functions. But here we are going to overwrite, anyway, that will be a stop address. As long as we override that address to print flag. So when we call exit, we're not really calling exit, we're calling print flag, right? That's the idea. So in this one, we're not overwriting the return address in the main function. Okay, so first you can find out where the GOT is. So I use object dump -r, you can find out the exit, the function exit's address is stored at this address. Okay, which means this is the address you are trying to overwrite. Okay, you are trying to overwrite this address with so basically there is an exit pointer. You overwrite with that. So I give you 10 minutes to work on this. Yeah. So as long as you have that idea, it's very simple now. Yeah. It's same as the previous one, it's just different address. When you do a NM on the binary, you do not find the address of exit. Not there. Because we don't know the address of exit, and the exit is not part of the program. Exit is part of the C library binary. Okay. But in the binary, there will be a global offset table that eventually will hold the address of exit. Yeah, and that you can use obj dump to get. So those are the only relocation addresses, and you can say exit is at this address. Oh, you're right there. When we do that, when we put that huge number in the format, in the ways, we are only piping into a small number. Yes, yeah, you're right there.
So that will be 7
Which one?
into 7, 9x into 7. No, I think it's at the 8th position, 9th
It's a nine.
position. So that'll have to be 7.
This should be 7.
Yeah, and that should be 292.
Okay. Oh, so previously was ready? Miscount there? Oh, okay, I miscount there. Yeah. So how many of you got this already? Okay, give you several minutes.
I'm just trying to finish the lot one.
Oh,
There you go. You brought it.
oh, got it. Okay, it's the same idea. The address of print flag at the beginning of the buffer, the format string. Then you put a percentage n there to replace the exit entry in that global offset table. Okay, that's the idea. So how do we defeat this kind of attack? So when you use that tool check sec, you probably already noticed that there are several features we haven't talked about. We talked about stack calorie, we talked about NX, we talked about PIE. We haven't talked about these two yet. So there is another feature called reload. This is to defeat the attack you just did. The idea is very simple. It doesn't use lazy resolving anymore, lazy binding anymore. So when at the beginning of execution, the linker will try to resolve all function addresses. So we're going back to the very beginning, which we want it to be faster, so we do lazy binding. And now we resolve all the addresses at the beginning of the execution. Then we just make the global offset table read only. So you cannot override that. Okay. Very simple idea. Those kind of ideas do not necessarily you can publish a paper, but they will be adopted in real world systems. And they are not necessarily that secure. There are all kinds of ways to bypass it, especially for reload. There is something called partial reload, where they only protect a part of that, which basically doing nothing because attackers do not, attackers only need to find one place you didn't protect. That's enough, right? But somehow those got adopted in real world. And there are many other pointers, many other places, like C constructors, destructors, init, feli. There are so many code pointers anywhere in the address space, and we can utilize them. At last, for the format string one, I want to introduce you to this paper. Very interesting. We talked about control flow integrity already, which assumes we know a legit control flow graph of a program. So for each indirect call, indirect jump, we know there is a valid set of targets we can jump to. Then at runtime, we're going to instrument some code. Before those jumps are called, we will verify if the target, the destination, is in that valid set range. This paper, control flow bending, published in 10 years ago, almost 10 years ago, proved that the control flow integrity approach we talked about can be defeated, especially with format string vulnerability. They have a section in the paper explaining that format string vulnerability is Turing complete. Basically, just using format string vulnerability, you can create arbitrary code execution there, which is very understandable because you can do arbitrary read and arbitrary write, right? Then you can write code at some places and jump to there. What they are saying, the control flow bending one is saying even that valid set, it's too, the valid set for each target could be too big. We just chain those valid functions together. We can also we'll also do something malicious. So the first author, when he published a paper, he was a PhD student at Berkeley, and now for the last several years he works for Google. He also published many papers in machine learning security, some of the very influential papers So this is a guy work on binary and machine learning security. If you check out his website, you find many interesting papers there. Okay, so that's all I have for full mastering vulnerability. Next week, we will talk about return-oriented programming, which is super powerful and super interesting. It's totally different from what we have learned so far. Any questions for today? All good? Okay. Then homework is due Friday for last homework. Then I will release this week's homework maybe tomorrow. And there will be two homework. One is this week's homework. Another one is for you guys to redo the challenges in midterm. If you captured all flags in midterm, then you don't have to do that homework. You'll automatically get 24, 45 points. If you didn't capture all the flags, you need to do the ones you didn't get. Okay, that's it. Okay. So I try to make it manageable. But there will be a little bit more homework at the second half of the semester because eventually we need 14 homeworks. I think we'll be 13 actually. Cool, and see you guys next week.
There is a homework 9, is that not the right one?
That's not the right one. I will push maybe tomorrow.